Welcome to 8.4 for Math 31, where we start to look at the derivative of logarithmic functions. And this can be a little tricky. Just like we've seen before, the derivative with respect to x of ln x is 1 over x. I don't mind this notation, but it really doesn't deal with the fact what happens if it's more complex than x, which is why I like these two forms, specifically this last form, a lot more. So the derivative with respect to x of the natural logarithm of u is 1 over u times the derivative of u with respect to x. And I think prime notation is even better. When we take d over dx of ln gx, it's 1 over g of x times g prime of x. And that's going to be really important that, typically what helps students, work with these problems is as soon as you see the derivative of a natural logarithm, put 1 over whatever's inside the natural logarithm and then deal with the derivative of the inside. And we'll see that as we work through the examples. The first thing they want us to show is they want us to prove that the derivative with respect to x of the natural logarithm of x is 1 over x. And the way that we're going to do that is we are going to let y equal to ln x. And the reason that that's beneficial is we can rewrite this in exponential form as e to the power of y is equal to x. And the advantage to this is that if we find dy over dx for either of those two, we know that this is going to be the derivative with respect to x of ln x. And hopefully, we get 1 over x. So the way that we're going to do that is we're going to take the derivative implicitly. So I'm going to apply d over dx, the derivative operator, on the left-hand side, and I'm also going to apply it onto the right-hand side. The derivative with respect to x of e to the power of something is e to the power of that same something times the derivative of the exponent. Well, in this case, it's y, so that's going to yield my dy over dx. Whereas on the right-hand side, the derivative with respect to x of x is 1. Well, if we want to know what dy over dx is, then we should manipulate it. And again, that's equal to 1 over e to the y. But if you track back up, sorry, I scrolled past it, we said that e to the y was equal to x. So if I substitute that back in, I get that dy over dx is equal to 1 over x. And that shows that the derivative of ln x is 1 over x. This is one of those things that we use a fair amount in chapter 8. One of the reasons we use the natural logarithm is I couldn't do this if this is y equals log base 10 of x. You can take the derivative of log base 10 of x. It is a little more cumbersome, and usually we recommend that you just change the base anyway. Natural logarithms and that Euler's number, right, the e to the power of, are very, very useful in calculus. They're almost kind of built for calculus because of how easy they can make differentiation. All right, so a couple more examples here. It wants us to differentiate the following. A is a product rule situation. You could put that x up into the exponent inside the natural logarithm. That is not a good idea. It is not very simple to take the derivative of x to the power of x. So instead, I am going to treat this as a product rule. So the derivative of x is 1. I'm going to multiply that by ln x plus x times the derivative of ln x. Well, the derivative of ln x is 1 over x. And I get that y prime is equal to the natural log of x plus 1. All right, not too bad. This is one of those lessons that most of this is just making sure we get comfortable, we get a little bit of, kind of paper time with the rules so that we can use those rules in application lessons later on. All right, for B, there is no product rule here. This is what I was talking about earlier, that if I'm taking the derivative of the natural logarithm of something, immediately I put 1 over the argument of the logarithm. And then I multiply by the derivative of that inner function. In this case, x squared plus 2x plus 5. The derivative of that is 2x plus 2. So y prime is going to be 2x plus 2 over x squared plus 2x minus 5. It is not one of those things that is particularly tricky compared to the other material that we've covered, but it's just something brand new, right? It's a new derivative. It's something we have to get used to. Logarithmic and exponential functions form a very real part of applications of math. All right, all of a sudden there's a trig identity coming out of nowhere, but we're not going to deal with it any differently than we would. I'm going to say that f prime of x is immediately 1 over the argument of that logarithm, and then I'm going to multiply it by the derivative of, in this case, cos, which is negative sine. I get therefore that f prime of x is negative sine x over cos x. I would be okay with that, but hopefully from all your trig, you know that sine x over cos x can get represented by tan x with the negative in place still. All right, for D, it is a power, or sorry, I guess it's going to be a chain rule. We have something to the power of 4. So that means that it's going to be 4 times that something, in this case, the ln of x, now to the power of 3. And then I would multiply by the derivative of the inner function. The inner function is ln x. The derivative of ln x is 1 over x. And then you can clean this up a little bit. Maybe write 4 times the natural log of x cubed, all divided by x. Easy to get lost a little bit in these questions. Make sure you're taking them really systematically and really, relatively slowly, just so that we do catch some of the, existing rules taking part. We fixed the typo. I don't know if it's still a typo in your notes. There used to not be that ln there. We can do this a couple different ways. You could just, put this as 1 over x over root x plus 1 and then use your quotient rule. But part of the reason that we like logarithms so much is that we can exploit those laws of logarithms to make that a much simpler function. And so the first thing I'm going to do is I'm going to use my laws of logarithms and rewrite this as ln x minus ln, and I'm going to write it as x plus 1 to the power of 1/2. And I'm going to go one step further. I'm going to say that this is y is equal to ln x minus 1/2 times ln x plus 1, and now I'm going to do the derivative because the inside of my logarithms is as simple as I can make it. So y prime is going to be 1 over x, that's the derivative of ln x, minus 1/2 times, okay, so we're doing the same concept here. I'm going to put 1 over the original argument, which is x plus 1, then multiply by the derivative of x plus 1, which is 1. So really trivial in that case, and I get that y prime is equal to 1 over x minus 1 over 2 times x plus 1. You could certainly manipulate that more and try to combine them as fractions, but like most, derivative lessons, we are focusing much more on making sure you can take the derivative itself. I hemmed and hawed about 2 parts or not, but I think I'm going to push through and we'll do this all as one part. So they show some other derivatives here, just other ways of dealing with this. This is what we've already looked at, the derivative with respect to x of the natural log of the absolute value of x. This one's a little different, d over dx of b to the x. It can be written in a different way. What I like to encourage students is to remember that we could or really should include that x prime in there. One of the ways that I like to deal with that is I'll typically write d over dx of b to the power of a function is equal to b to the power of that function times the natural log of b, and then multiplied by the derivative of that function. And it's the same concept with this last one. This is that base e, that I could write this as d over dx of log base b of f of x, and that's going to be equal to 1 over f of x times ln b multiplied by f prime of x. These are on your formula sheet. One of the things you could do with this last one is change the base. D over dx of log base b of x, I can write, and maybe I'll just do the logarithm, I could write as the natural log of x over the natural log of b. It's supposed to be a natural log. I'll try that again. I could write that as a natural log of x over the natural log of b, because I've just used my change of base, and then I could take the derivative normally. Nothing wrong with doing that. It's certainly part and parcel of looking at these, is that we're basically just kind of following the recipe given to us on our formula sheet. So they want us to differentiate a couple. This is y equals 2 to the power of x squared. That means that dy over dx, and I'm following that form previously, is going to be 2 to the power of x squared times the natural log of 2, and then multiplied by the derivative of that expression, which is 2x. And so dy over dx can be written as 2x times the natural log of 2 times 2 to the power of x squared. There's another way of doing this called logarithmic differentiation, which we're going to cover a little bit later on. But for now, we're going to practice using those forms that are given to us. I am going to use a little bit of a log law here. I'm going to get that exponent into a coefficient. So it's 4 times log base 10, which we don't even need to write, but it's there, of 3x plus 1. This is then going to be equal, when we take the derivative, y prime will be 4 times, so it's going to be 1 over the argument of the logarithm, so that's 3x plus 1 in this case, times the natural log, I'll put a bracket around that, sorry, the natural log of the base, which is 10, and then finally we're going to multiply by the derivative of the inner function, which is 3x plus 1, so we multiply by 3, I can clean that up a little bit, and I get 12 over 3x plus 1 times the natural log of 10. It can be a little confusing following these forms. Make sure you have your formula sheet with you or handy as you work through this. Most of this is just making sure we can follow, again, that recipe on the formula sheet. All right, Last one here for this lesson. It wants us to find the absolute max value for this function ln x over x. I'm going to write that function, well, no, I'm not going to change it. Let's use the quotient rule instead. So if we're going to find the absolute max, what we need to know is the derivative, because the derivative, sign chart is going to help us with that. So f prime of x is going to be, the first thing I'm going to do, sorry about that, headset fell off, is I'm immediately going to take the original denominator and I'm going to square it, right? This is just the quotient rule. Then I'm going to take the derivative of the numerator, which is 1 over x, multiplied by the denominator, minus the numerator, which is ln x, multiplied by the derivative of the denominator, which is 1. Now we should clean this up a little bit. 1 over x times x is 1, so I get 1 minus the natural log of x over x squared. All right, what we need to do then is we need to find the critical numbers. Now, the first critical number that should be, I hope, pretty clear and easy is 0, right? Now, the trick, though, is 0 in the domain of this function. And it's not, right? If we take a look at the natural log of x, immediately x must be greater than 0. And it can't be equal to 0 either because x is in the denominator. So the only critical numbers that are going to take part in this are the 1 minus the natural log of x when that's equal to 0. That's my numerator. To solve for this, I get that 1 is equal to the natural log of x. I'm going to switch to exponential form. I get e to the power of 1 is equal to x. So my critical number, the only critical number, is going to be e. Now, a lot of students don't like the fact, well, e is a letter, not a number. And usually by calc, we're over that particular, little mental problem there. But a lot of students don't like, what is e? How close is it? How large is it? I would encourage you to remember e is 2.7. It is very, very similar in that to pi. It is a value. It's certainly not exactly 2.7, but 2.7 is a decent approximation to talk about that. So what I'm going to do here is I'm going to create our sign chart. So I'm going to draw the number line. I'm going to put e kind of right in the middle, I suppose. Draw a vertical line down there. So this is going to be the interval e to infinity. This is going to be the interval 0 to e. The function does not exist when x is less than 0. And then what I'm looking at there are two factors. There's 1 minus the natural log of x, and there's also x squared. And then what we're going to be doing is we're going to be evaluating the sign of f prime of x. X squared is always positive. I mean, these are only positive numbers, so that certainly works as well. When x is in between 0 and e, what we have to consider then is that we're taking, let's take a look at the natural log of e is equal to 1, right? If we think about what that natural log is telling us, it's e to the power of what gives us that. So when x is bigger than e, so let's look at the natural log of 3. I know that the natural log of 3 is going to be bigger than the natural log of e. Now that means that 1 minus a number larger than 1 will give me a negative. 1 minus a number less than 1 will give me a positive. So f prime of x is positive from 0 to e, and it's negative from e to infinity. Now, because we have that situation where it's only increasing and only decreasing, we know that there is a maximum at x is equal to e. And moreover, we actually know that it's an absolute maximum because this graph is only increasing and decreasing. I'm going to say then that my absolute max is at x is equal to e, but we probably want to know where that is. So if f of x is equal to the natural log of x over x, then f of e is the natural log of e over e, which is 1 over e, or e to the negative 1. That's perfectly acceptable. But what that means is that our absolute max, the actual coordinate for it, is going to be e comma 1 over e. I always encourage students to maybe take a look at the graph and make sure that that makes sense. So I'm just going to kind of pop it up onto my graphing calculator here, and I'm going to make y equal to the natural log of x divided by x. And the Zoom standard should work perfectly for this. When we graph it, we do get a bit of a weird kind of looking function, but it's pretty clear to see that it's only increasing and then only decreasing. To find that maximum, that second trace max, option number 4. The left bound, I'll just make sure it's on the graph, so 0.3. The right bound, I'm going to go past e, which is about 2.7, so 3.6, I'm well past, and then I'll guess. And I get that this happens at 2.718, which should look familiar, and then 0.37. I'd like to take those values and just show you that if we look at that x and y, to get e on your calculator is a little bit annoying. It's second function natural log because they're opposite operations. So e to the power of 1 is the 2.7182. A little bit of a rounding error in our calculator, that happens. And then when I do 1 divided by e, I get very, very close to the value, right? In fact, it is the value, which is nice. So it did 1 over e a little bit better than it did e to the power of 1. All right, definitely a pretty important lesson. Derivatives of exponential functions happens quite a bit. Make sure you practice this. You have your formula sheet. Any of those formulas that aren't on there, please feel free to write on there. Your formula sheet should contain all those kind of basic differentiation rules. Please do all of this assignment. I know it can feel a little tedious, but the only way to get comfortable with derivatives is by doing derivatives.